Let's arrange these compounds in order of decreasing acidity, meaning from the most acidic to the least acidic. Now, the first thing that we do is we choose the acidic hydrogen. And the acidic hydrogen is going to be next to the oxygen of the carboxylic acid. So all of those hydrogens that I am highlighting, these are going to be my acidic hydrogens in there. Change each one of them into a conjugate base. So we're going to change it into a conjugate base. Now notice that when I chose the acidic hydrogen for the first structure, I didn't choose the hydrogen that is connected to the oxygen here, because between an alcohol, a hydrogen that is close to the oxygen, this is an alcohol functional group, and an acid functional group, the hydrogen connected to this oxygen is going to be way more acidic. This is why if you have a base, the base will come and take this hydrogen and create the conjugate base. For all of these structures, the difference is the group that is connected to the cyclic compound that you see. The cyclic compound is called benzene. So let's highlight the benzene. So benzene is this, and it is actually common in all of these structures in there. So whatever is on the benzene is the difference in there from one structure to the other. All of them, they contain the carboxylic acid group. All of them have a benzene, but the difference is the group that is on the benzene. So let's finish drawing the conjugate base for each one of them, and then determining what type of groups are on the benzene. There are two different types: electron donating groups and electron withdrawing groups. So we have the NO2. Let's put another NO2 in here. So we have a different structure. Okay. And then a carbon double bond O. Here you go. So all of these are the conjugate bases of the acids above. The difference is, as we mentioned, is in the groups that are connected to the benzene. So this benzene has a group OH on it. This one has nothing on it. This one has the NO2 on it. And this one has two NO2s in there. Okay, so let's study the nature of these groups. Oxygen has lone pairs. It does have two lone pairs in there. So oxygen is considered to be, whenever it is on the benzene, it's an electron donating group because it can donate electrons by simply doing resonance in this case. So you will have resonance across the benzene. You're donating electrons now. To look at the stability of the conjugate base. Normally, conjugate bases are stable whenever the charge is delocalized. So if you have an electron donating group, and that electron donating group is giving electrons, so you're adding electrons to the negative charge, you're no longer distributing the charge, you are adding to it. So that is going to decrease the stability of the conjugate base, and it's going to make the acid less acidic. So by definition, electron donating groups, they decrease the acidity. Electron donating groups, call those electron donating groups. We're going to hit on electron donating groups as we proceed, but the idea is that electron donating groups, they should have lone pairs. So if they are present directly next to the benzene, then those lone pairs are going to undergo resonance across the benzene, giving the conjugate base electrons, decreasing its stability. So electron donating groups decrease the acidity of the acid by simply decreasing or making the conjugate, its conjugate base less stable. On the other hand, if you have an electron withdrawing group. Now, what is an electron withdrawing group? To look at it, you have to draw the Lewis structure of NO2. And the Lewis structure for NO2 is a nitrogen with a double bond O and an oxygen in there. Now notice NO2 is a zero charge, so this is why I have a negative charge here and a positive charge there. That is going to satisfy the valence electrons. Now notice the difference here. This oxygen has lone pairs, and the lone pairs can be donated to the benzene by simply doing resonance. This nitrogen has no lone pairs to donate. In fact, it is a positive charge. This means that it has no electrons to give to the benzene. If I want to compare the electronegativity of this carbon here, which is an sp2 hybrid carbon, with the nitrogen, I know that nitrogen is an electronegative element. So the direction of polarization or the pull of electrons is towards the nitrogen in there and then towards the oxygen. So notice how the nitrogen and the two oxygens are stealing electrons away from the benzene. So if they are stealing electrons away from the benzene, they are also stealing electrons away from the oxygen. So this is how the charge is delocalized. That is going to stabilize the conjugate base, and it's going to make this acidic hydrogen more acid, more acidic. The more electron withdrawing groups I have, the more stable is the conjugate base because the charge will be more delocalized, and the more acidic is the hydrogen, or the more acidic is the acid. So by definition, an electron donating group decreases the acidity of the acid, and an electron withdrawing group increases. This is an electron withdrawing group increases the acidity of the acid. Electron withdrawing groups, they have a positive charge. So normally what they do is they take electrons away from the benzene. Electron donating groups, they have lone pairs, so they give electrons to the benzene. And when they do that, they destabilize the conjugate base and they make the acid less acidic. Electron withdrawing groups, they stabilize the conjugate base by the distribution of the charge, and they make the conjugate or the acid more acidic. The more electron withdrawing groups you have, the more acidic it is. So if I want to arrange the acidity in here based on the most acidic first in a decreasing order, then definitely this is going to be the most acidic structure, and then this is going to be the second acidic. Electron donating groups, they decrease the acidity, so this is expected to be the least acidic because of its conjugate base that is not stable. So this is going to be more acidic, and this group is going to be the least acidic. There are different types of acids that we are going to use in organic. We have the halogen acids. We have the acetic acid. This is the weakest type of acid compared to all other acids. We have sulfuric acid, H2SO4. We have the phosphoric acid. These are the ones that we will be using. Also, we will be using a very strong acid, which we call the para-toluene sulfonic acid. Toluene is whenever you have a benzene connected to a CH3. Para is a term that we use whenever positions 1 and 4 on the benzene are occupied by a group. So we use the term para in there. You don't have to worry about the naming much because we're going to hit on that as we proceed. This group that is highlighted, we call it a tosyl. So we abbreviate this acid by a TSOH. Whenever you see it, just know that you are working with a strong acid, and this is going to be the acidic hydrogen. There are two types of common bases: negative charge bases and neutral bases. The negative charge bases, they are always strong bases. There are some exceptions we're going to go over, but in general, negative charge bases are strong bases. The negative charge can be on the oxygen, on the nitrogen, on the hydrogen, and on the carbon. The most stable base or the most basic base is whenever the negative charge is on the least electronegative atom. Because whenever you're looking at the trend of basicity, it's the opposite to the acidity. So as the electronegativity increases, as the basicity is going to decrease within atoms in the same period. So we're expecting a carbon to be a negative charge when the carbon is negative charge, although this is a less stable conjugate base in there, but it's going to be the most basic. Between nitrogen and oxygen, nitrogen is more basic than oxygen because nitrogen is less electronegative. So the lower the electronegativity, the more basic is the base. Whenever you're working with the hydrogen halide acids, now because of the structure of these acids and because these acids are extremely strong, their conjugate bases are going to be extremely weak conjugate bases, even though these conjugate bases, they carry a negative charge, but because they come from a strong acid, they are going to be weak bases. This is the only exception to the negative charge rule of the base. So all negative charge bases are strong bases with the exception of the conjugate bases of strong acids. Those need to be weak bases, even though they carry a negative charge. The second example of bases are neutral bases. And those neutral bases are really weak bases. Nitrogen can be zero charge. Also, oxygen can be zero charge as well. So in this case, if I have like an alcohol, this is going to be my nucleophilic site. And the oxygen is a zero charge. Similar, I can have water also to be an example of a neutral base. So all of those are examples of neutral bases where the oxygen carries a zero charge or the nitrogen can carry a zero charge as well. Regardless which one, both are examples of bases. After all, remember guys, that base is a source of electron. So every time you're looking for a base, you're looking for the lone pair. Whether you have a negative charge or whether it is neutral, lone pairs should always be present. Nitrogen bases are way more basic than oxygen bases because nitrogens are less electronegative. So the point is, when you are given a reaction, you need to locate where your base is, where your acid is. You need to know what type of base you are working with. Because if you are working with a weak base like this one, you need to use a strong acid for the reaction to move forward.